Hello, I'm Substack from the internet, and I'm here to talk about mad science inventory. So I have on this wonderful lab coat, so that's how you know I'm a proper, trustworthy scientician. And so I'll just be talking in this talk very briefly about how I go about mad science. So there are a bunch of us in the Node.js community who really have these values of crazy freedom and excessive modularity and just whipping things up that seem like a bad idea until some of them are actually, good ideas in the long term, except so this is a really big thing in Node.js, and I think that's a really great part of our community. But like, what is mad science? I mean, that's a pretty squishy definition. So I think mad science breaks down into a lot of different kind of loosely correlated ideas. So in one sense of mad science, it's really the ability to harness the powers of the computer to sort of like give esoteric incantations into it that are very terse, that do something incredible that you wouldn't expect. In another sense, mad science could be about being able to just recombine things in completely different, surprising ways. And it's really just about this kind of level of computing that's very distinct from like the standard corporate way, which is just to plug it some giant framework and to just like basically be like an X-ray technician, where maybe you know how to fiddle the knobs, but you don't really know what's going on or like how to fix it. So a big part too of this mad science idea is that there's all of this great prior art, and wouldn't it be nice if we could actually use it? For most of computing, you really can't, or it's very difficult, and most of our time as programmers is spent working around that fact. So like, there's all of these mathematical libraries written in Fortran that nobody even knows how to write variants of anymore. It's just like, that's the version, and those people have all like, they're all in retirement homes, and nobody knows how it works. But what's really great about our community is that we have very robust package managers, and we have this culture borrowed from earlier systems like Unix and CPAN of making very focused small pieces that we can assemble into big things. And assembling small components is really important because it means that, just like in Sliders, the 1990s sci-fi television program, you can just take a system as it is, and you can just change one thing about it because that system is just decoupled such that you can just flip a switch, and now instead of the British ruling North America, it's actually the French, and everybody eats croissants and bagels all day or something. So one really other surprising thing about mad science in the Node community is that there's this surprising paradox where the more modules you write, the more modules that you realize need to be written that are missing. And so it's not even like you're hitting limits of scarcity, you're hitting like these modes of abundance where everything is just more open because more exists. And that's kind of, I think, what's leading to a lot of the exponential growth on NPM, for example. So what makes a good tool? We should have a good system for evaluating like what things we should be valuing in our basic tools. So I think this idea of orthogonality is very important for that. Like, we should have tools that do one thing well, but why? So it's all about what trade-offs you want to consider whenever you're building a tool. Like, there are certain ways of doing things that are kind of inherent to any problem domain, but the more orthogonal your tools are, the more free you are to sort of recombine things so that they actually match all of the trade-offs inherent in the domain. So I kind of think of it like use case coverage. Like, we have this idea of code coverage, but we should also have this idea of having enough basic low-level primitives that we can really cover all of the possible cases without having to rip things apart or having to re-implement things from scratch, because that just makes us all much less efficient and much more miserable. Another important thing is that if you want to become an aspiring mad scientist, one of the best ways to do that is to go and just start writing your own code and then going and using other people's code. And as you do that, you sort of recognize some patterns. Like, you realize that you really like some authors and you really hate other authors, and when you're doing a search, you can just pick up on that and not even bother with most of the results because you see one from an author who you really trust. Some other things that you should, of course, be wary of is like stars and the number of watchers on GitHub or that kind of thing, because those can be quite misleading, and I think it benefits everyone to sort of figure out what things you personally care about, because everyone is going to have a different background and experience, and it's really worth your time to sort of figure out what ideas resonate the most with you, and then it'll just pay dividends whenever you go to search for surreal stuff. So I like to liken this whole process of finding and composing modules in terms of dumpster diving. So I built this whole underwater ROV thing in 2010 in Alaska, almost all from parts that were scavenged out of the dumpster. And what's really great about that is because there's all of this refuse lying around, you don't have to worry about making a mess. So you feel really free to just kind of experiment and do whatever. And you also don't have to worry about how much it's going to cost you to try and experiment, because you just have all of these components. And what we have with open source is very similar to this, because we have all of these great technologies, and we can just recombine them in all kinds of ways. So example time. So I have a ton of these. So the first thing I can show is this multiplex library. So this is just an example of a recent project that I've been working with some people on. So multiplexing is really cool, and it's actually a very powerful idea that you can use for lots of mad science. So the basic idea of multiplexing is that you have multiple input streams. These can be readable or writable, and you only have one transport stream. So for example, maybe you have one WebSocket connection because the browser doesn't let you make very many of those, and you need to economize that, or maybe you just, for whatever reason, can only talk to the rest of the internet through a pigeon, and so you need to put all of your communications into that pigeon. So everything has to be packed down into a single data channel. So an example of this that I think is very simple to understand is saving the output of a command. So a process that you spawn can write to standard error, or it can write to standard out, and it also has an exit code. So you can think of standard out and standard error as just channels that you need to capture if you want to replay it later, without having the error messages be out of band with the just standard messages. And if you also don't want to add colors directly into the stream and save it all out to something, because maybe you want to also render it as HTML or whatever. So anyways, we can do this. So here we can just spawn a child process from process argv, and we can just make a little stream. So here we're just piping to standard out. And then we can take the output of the process. So we're capturing standard error. We're stuffing it into a little buffer, and the first byte we'll use for the file descriptor, basically. So 2 for error and 1 for standard out. And then we'll just pack 2 bytes with the length, because buffers probably don't get over 65,000 or so. So this will basically be what we need, and so we do the same for standard out with a different data channel, and we can run this. So if I just run this program and I give it a command, cool, it prints some ASCII garbage there. We can look at it with cat-v to see that, yeah, it's actually it's A, which is 1 for file descriptor 1. So cool, that's working. But that's kind of a lot of code, right? It would certainly be great if we could just depend on robust abstractions that already exist. So it turns out we can. There's this module called Multiplex. it's quite similar to some other libraries that have already existed, like I've talked about MuxDmux in the past by Dominic Tarr here, but Multiplex just has a really nice compact binary representation, so it's better for some use cases, and like it's very important that we have these kinds of things, like that we don't just have one multiplex library so that we can better cover all of the possible use cases. So anyways, we can spawn this process, and then instead of writing to standard out and doing all that buffer byte twiddling ourselves, we can just create 2 data streams and pack them into standard out. And if we do that with the same input, we get this, which is pretty cool. So, and we can look at the output. It's approximately the same. It's a little bit different, but there's like an extra byte of framing. But so that's pretty useful. So then what if we want to unpack? This is the nice thing. Writing an unpacker for that binary stuff ourselves is much harder than packing it in the first place. So we can get the benefit of this code already existing and already being useful just by creating 2 streams, piping them to standard error, standard out in this case. So we could take the output of our first program and pipe it into our unpack program, and then we'll just get the normal output, which is not actually that interesting until you start to do things with it. Like here, we can use another package entirely for colorizing that stream. So the colorize module doesn't have to know or care about whatever is happening elsewhere. It's just completely decoupled. It exists in the ecosystem of all possible packages. And this one happens to exist. So that's very useful. So here we can just pipe into our colorizer to turn standard out to green and standard error to red. Or we could choose whatever other colors we want. So run that program. Oops. To run the right program. There we go. There we go. It's green. So that's because we have a program that just has standard out. But if we make another program, like if we run bash with a calendar and then a made-up program, that should give us some lines on standard error. So cool. We were getting red. We're getting green. It's working. That's basically multiplexing. But wouldn't it be cool if we could also do this kind of stuff in a even more modular way? Like we can, every time that you learn something, I think, we should be encapsulating that knowledge into reusable abstractions so that everyone can benefit, and we can pool and amortize our resources to benefit everyone. So if we do that, I've taken this whole program and I've made a separate program called shellpack, and we can give it the same arguments and then run that back through an unpacker. Whoops. Well, anyways, that works, but yeah, you get the idea. So this is just one example of how I tend to go about building applications, but I mean, this is a relatively restricted example for the kind of mad science way of doing modules and doing modularity, but you can also do this for something like a boring accounting website. And I think it's a good idea that we should do this, because I think accounting websites are the most in need of this kind of intervention. So as you'll notice, I'm just in an empty directory now. And let's build a web server very quickly. So first thing we can do is just require the HTTP module, call http.createServer. We get the request, the response, and we're up and running, basically. So we'll listen on port 5000, we'll res.end beep boop. So that's pretty cool. I'm sure you've all seen this. You run it, you curl it, and it says beep boop. Cool. We've all seen that before. So that's not interesting. I mean, what people like about frameworks is they're very handholdy, and there's a common answer to any kind of question you could ever have. But actually, what we should be doing instead, if we're going to be proper mad scientists with a proper method of empiricist methodology, is we should actually be figuring out what our requirements are first, and then finding very narrow pieces that just satisfy those requirements. So say we need to statically serve some files. Well, we just pick a module off of NPM, like this one, called ecstatic, and we can just use that. So you just give it a directory, make the directory, and we're up and running. So just do that, and now we have a server like before that will serve static files. Cool. So what if we want to do some other things, though? I mean, this isn't especially interesting. And of course, as you build a big application, this approach doesn't really scale as well. But it turns out that you can do pretty much everything that you do with a big framework approach with very small decoupled modules. So in this case, we can use the router from Express, which is just published completely independently as a package called routes, and build a router by adding routes directly. So router.addRoute, like foo, function recres, and then you just have to remember or find a module to apply this little bit of boilerplate. So you can do router.match rec.url if m return m.fn recres m.params. That's all you need to do. And then we'll still use ecstatic from before, just like that. So cool. So now we have a custom route. We can run our server, and we can curl it, and that's our ecstatic stuff, and now there's our custom route. Wow. So that's all well and good, and another fun thing is we can do the same approach, the mad science approach, for databases. So there's going to be some more talk about this later, but all that you need to do to have a mad science database is just pick one of the many great modular databases like LevelDB and give it a directory, and you're up and running. So now we have a database. So we can put stuff into it. We can have some records. Like here, we'll do a batch. So we'll put like a username, user Substack, value beep boop, and we'll maybe put another record for another user. So user Dominic. There we go. So now instead of serving that from our route, we can just do a create read stream, like so. Give it some restrictions on what the input should be. So user to that, and now we've got user records. So then you just pipe that to like a stringify or whatever, and pipe that to the response, and we're up and running. So anyways, you do just basically that, and you'd have a web server. So this approach, I think, is really valuable, but how can we make this more mad science, right? We have all of these components, so now what can we do with it that is just completely crazy? So one thing I have for doing this kind of stuff is called Dataplex. So Dataplex basically takes that router that's normally for HTTP routes and lets you expose that on any streaming interface. So it gives you the same kind of benefits that you would use for organizing streams that you get for organizing your HTTP routes. So basically, some problems with using multiplex directly are that you have to like manage the IDs by hand. So you have to like establish out-of-band communication to pick good names and that kind of thing. So to get around this, first of all, we can just write an onStream function. We can spin up Dataplex, and then hook up with the duplex pattern. We'll just like pipe our stream into our Dataplexer and then pipe that back out to our stream. Create some routes, like here we have ABC and T-Rex, and we'll maybe serve some just text files to our response. So here we have abc.txt and trex.txt. So if this will be our server, and then we'll make a client, and all that the client has to do is it'll just use the Dataplex library and wire that up to a TCP connection on port 5001, and it'll just do plex.open with the route name, and you'll get the response. It's just like standard duplex stuff. So I'll run the server, and then I'll run the client, I think 240, blah. There we go. So it's just streaming some text from some files. So nothing too mad science yet. So what else can we do? Well, we can actually make all of the kinds of things that you would use like ORMs and models for in this streaming abstraction instead. That's more abstract. So here we can do like with LevelDB, like before, we can stream out some users to like a JSON result and just pipe that through a stream. Or we could use like a content addressable blob store to store like just uploads from users. So we can do all this kind of stuff, and it's not actually all that much code, but the amount of code that we're using from the community is actually kind of incredible. So the other thing that we can do with all of this craziness is let's build the most boring possible application. Let's build Jenkins. So what would that look like? Well, we can use all of these abstractions that I was just talking about to build a batch queue for doing shell scripts. So we can use LevelDB like before. We'll set it up with Bytewise for our encodings and set up a content addressable blob store for storing the results and storing the images. We can use the HTTP module with a router like before and create a little server that will just do stuff with our router. That's the standard boilerplatey stuff. So we could have like a create route for responding to jobs, like putting a pending job in the queue and then removing it correctly and all of this stuff. And then we can also do all of the other boring stuff, like make a route for lists, make a route for like reading a blob out. But the nice thing is, because we're doing things in a mad science, in a modular way that's just based out of simple primitives that we're just requiring directly, we can actually encapsulate all of this into packages. So not only would we have to write all of that code that I showed you, but we'd actually have to do the running too. And it's really best to put these things in reusable abstraction. So here, this is a new package I've just recently made called BatchDB that sort of encapsulates all of that annoying stuff and just stuffs it all in one place so that you don't have to look or care about it. But actually, and that does simplify things a lot, and it handles all the running and everything. But we still kind of have a lot of ugly code here. So we have all of these routes and this HTTP endpoints. But actually, why can't we do the same thing for those HTTP routes? So, well, first we have to also write the part that does like running the shell scripts and capturing the standard out and standard error. So we can use this multiplex approach that I was talking about earlier to do that. And we can use another package called BatchDB shell for that. But then we can get rid of all of that code just by stuffing it into a separate module, throwing it on NPM, and forgetting about it. So here we've got, this is now our entire build server that does, that just runs bash commands that you throw at it, saves the results to a blob store, does all of the pending correctly. So if you kill it, it'll restart. And we're just using simple primitive interfaces. Like nothing is terribly complicated or especially like hard about this. It's all super modular, and we could do the same approach if we want like a UI. So we would just write a UI module and have it handle routes itself and like have single responsibilities and all this kind of stuff. But this isn't yet very mad science. So how could we make this properly mad science? Why don't we turn our Jenkins server into a botnet? So how do we do that? And why don't we make the bots browsers so that we can just run arbitrary code and treat them like a data farm? So it's not actually that hard to do this, but you have to sort of take a step back and decompose things properly. So I made this module called Botnet Pool that just, all that it does is basically this. So it's this little thing that listens on a WebSocket, or it could listen on WebRTC or something. And it basically just packs everything into the format that the multiplex library expects. And this is it. And then it just like evals whatever jobs are posted to it over the WebSocket, which uses Dataplex, which uses the multiplexer in multiple ways. And so we've got this big tower of complexity that's like handled for us in this very robust way. And of course, we can just get rid of all of that code, stuff it into another module, and then like build on top of that. So this is all the browser code that we need now to make our botnet. So here I have it running on a port 5002, So if I post a job to it, so here I'm just piping some JavaScript code, so it's console logging a thing, and then doing a ABC, which doesn't exist, so that'll throw an error, so that should be in our error stream, and then I'm just telling it to exit. So we'll just post that to our job server, and now, oh, hang on, let me just, oh no, it's completely failing. Well, this was completely working earlier, so. What I can show you is just what the interface looks like. So, oh, hang on, I think it's hiding it. Oh, right, I was using the wrong port. So, use the right port. There we go, we have a job ID. We can curl localhost for a list of the jobs. We can read the result by the blob ID. So let's see, list result. Oh, there's no results because I need to refresh it. Yep. Well, basically, we've just about got Jenkins working in browsers. So, just I think the thing I want to close with is just like consider the amount of use cases that you get when you start tackling problems in this manner, where you're breaking everything up into super small pieces. So not only do we have our build server, but we have all of these other systems in place that we can like throw down at a moment's notice. Like we have our batch queue, we can like run shell scripts, we can capture the standard out, standard error, we can pack like things up with multiplexing, we can make a botnet. We have all of these possibilities from like relatively few packages that we needed to make to get there. So the other thing that I want to mention briefly is that I think that our approaches and ideas in software should sort of have this notion of back pressure. Like when you make an idea or you gather a list of requirements, you're not really doing that in a vacuum, right? You're doing that based on what exists in the community already, and what exists should inform what your requirements are and what directions you drive things. And then you can also throw those things back to the community, and then everyone can benefit. So that's all I have to say. Thanks.